Welcome back. In this video, we're going to take a look at some other properties that relate the dot product and the length or magnitude or norm of vectors. And let's just pick up with the result that we previously established, and it's the idea of the angle between two vectors. Um, so if u and v are both non-zero, right, then theta, the angle between them, we can find that theta by using this ratio, right? That the cosine of theta is u dot v, so the dot product of u and v over the norm of u times the norm of v. Now, since these two things are equal, we can, and I think we probably have more experience with the cosine function than we have with this ratio. I mean, it's not a complicated formula, but we know a lot of properties that come from our cosine function. And one of them is this. So for theta being real, right? So no complex numbers inside our trigonometric function. But whenever theta is a real number, right, which in this case it will because it's an angle, we know that the cosine function is bounded. So we know that this is true. And I'll write it like this, that the cosine of theta is between -1 and 1, right? So like this. But then now I know that for these non-zero vectors, this cosine of theta is actually the same as this ratio. So I'm just going to drop that in between the -1 and 1. So this implies that -1 is less than or equal to u dot v over the magnitude of u times the magnitude of v, and then again that is less than or equal to 1. And then we can multiply through, this compound inequality, multiply through by the denominator, and then we get this. The negative of the norm of u times the norm of v is less than or equal to, our dot product is still stuck in the middle, right? And then on this side, we have the positive of that product. So it will be the norm of u times the norm of v. And if you look at this inequality, you might have a vague recollection about a property of absolute values. So, whenever you have a quantity that is kind of stuck between some other quantity and it's negative, then this means, so the next implication is that the absolute value of what's in between or in the middle there is then less than or equal to the positive of this. So the norm of u and then norm of v, right? And again, it seems like a simple thing, but this is such a profound inequality, and it's used a lot in the area of analysis. Just for example, in advanced math, and it has a nice name, and it's named after two mathematicians. It's usually referred to as the Cauchy-Schwarz, so it's be uppercase S, inequality. Yep. So that's the first thing that I want to mention. Next thing I want to mention is, so previously we looked at, we used a triangle to come up with some, in fact, it was the triangle that kind of led us to this ratio. So let's look at another triangle that can be defined by vectors. And I'm going to define it this way. And again, I'm not going to assume any particular or special relationship between these two vectors, but let's say this is u, and then let's say this is v, and now I want to look at the vector u plus v. So not u minus v, but u plus v. So u plus v, I could actually create, in fact, let me do this. I'm going to create a parallelogram, right? Now you may have seen this before, that this diagonal of the parallelogram right here is going to be the sum of the two vectors. And then if I just translate u over to this side, so I'll get a u there, and then what I have here in the middle is u plus v, right? So just a little bit of vector geometry, if you will. So what I'm going to do is just take out the triangle now that looks like this. So we got our v there, Gotta put my arrows and stuff. So we got our v vector, our u vector, and then here is u plus v. And again, I'm interested in the norm or length of these vectors, so I'm just going to say, okay, let's just look at their lengths, right? So then all of a sudden the arrows don't really matter that much. But there we go. So a natural question is, how do these three norms relate to each other, right? Again, notice what we have is we have three sides of a triangle, right? Well, I'm going to start with what appears to be the longest of the three, right? Which is the u plus v, right? Again, I say longest because we don't really have any numerical way of verifying that, but yeah, it just seems like, okay, this diagonal right here just appears to be long. So I'm going to start with that one, and instead of working with the expression for the magnitude as it is, I'm going to look at this magnitude squared. So I'm just going to consider this expression and think of all the things that we can do. Now, one of the earlier properties that we talked about with the dot product is that if you take the dot product of a vector with itself, you will get the square of the magnitude of that vector, which is what we have right here. So this can be written in a dot product form. So this is the same as u plus v dot with u plus v. Right? Yeah. No matter how complicated the vector is or the expression that we have for the vector, once we take the dot product of a vector with itself, it's always going to be the magnitude squared. And then again, let's use some previous properties of the dot product. So the distributive property, I can apply that one, and this would be u dot u. So basically what we're doing here is foiling out a dot product of a sum of vectors, right? So u dot u, and then in the middle we're gonna have plus u dot v, and then plus, again now with the v, so v dot u, and then finally plus v dot v. Now, again, all the way we can sort of manipulate this expression is to say, well, this right here is just the magnitude of u squared, right? That, again, that's one of our properties. In the middle, now we had said that the dot product is commutative. So these two terms in the middle are the same. We have two of them, so I'm just going to write them as 2 times u dot v, and then over here this would be the norm of v squared. All right, so it kind of looks like your perfect square expansion, but no, it's got dot products and magnitudes and stuff in there. Now, so what we know for sure is that the first term and the last term are always non-negative, right? In fact, if we assume that u and v are a non-zero vector, then we can say that the first term and the last term are definitely positive. But we can't say that about the dot product. It may or may not be positive, right? Because that depends on the angle between the vectors and going back to our ratio. But what I can say is if I then take the absolute value of the dot product, or why would I do that? Because, dear viewer, I'm going to use our Cauchy-Schwarz inequality to come up with this other property that I'm trying to get to. So anyway, so what I'm going to do is I'm going to replace what's in the middle by something that's bigger. So then it won't be an equal sign, it'll be a less than or equal sign. And then I will have, that will stay the same. And then I'm just going to put absolute values around the dot product. Just to ensure that that is positive, right? But once I do that, I would have, if the dot product is already positive, then we would have equality. If the dot product was negative and then I make it positive, then we would have something greater. That's why we have the greater than or equal there. All right, and then let's apply the Cauchy-Schwarz. Now, notice what the Cauchy-Schwarz says is that the product of these two norms is always going to be greater than or equal to the absolute value of the dot product. So if I put something even bigger in place of the absolute value of the dot product, again, I'll get another less than or equal to, and then I'll have this. We got squared, and then we'll have plus 2 times the magnitude of u times the magnitude of v plus the magnitude of v squared. And I mentioned the perfect square formula, right? I mentioned the perfect square formula earlier. And if you look closely, it does look like it. You got something squared plus something, 2 times that thing plus the other thing, and then plus the other thing squared. In other words, I know it sounds like gibberish what I'm saying, but what we have, if we just use a and b, this is a famous formula, right? Here we go. So you just do that. So basically, just put wherever there's an a in this formula, just put the norm of u. Wherever there's a b, just put the norm of v. So then I can actually factor this expression here. So the next line now is going to be an equality because that's just factoring. And then I will have the quantity, and then I'll have the magnitude or norm of u plus the magnitude or norm of v, and then squared. All right. So let's put this all together, right? Again, we're utilizing a lot of properties here. So this implies that the norm of u plus v squared is less than or equal to this last thing at the end here. It could be equal, but it certainly can't be bigger, right? So it's always going to be less than or equal to what I have here in parentheses. And now the thing is, so what is this? Is this a good property? I think so, but we can actually simplify it a little bit more and get a simpler property to look at. Now, what's on both sides we have non-negative quantities. So it will be impossible for the thing that's being squared on the left to be negative and the thing that's being squared on the right to be negative. So because all these quantities are non-negative, just take the square root of both sides. So this implies that the norm of u plus v is less than or equal to the norm of u plus the norm, let me start over, norm of v, like that, right? And so let me go back. I think I can get it all on the screen now. So look at what this property is saying with regards to our triangle. It is saying the length of the longest side is no greater than the sum of the two smaller lengths. So that's how you say it in words. And that property has a name, and we call it, for obvious reasons, which is why I wanted the triangle there, we call this the triangle inequality, right? And it just shows up in so many contexts, right? But all of these properties, right, they have some kind of, especially when you're talking about vectors in Rn, there is some kind of geometric way of helping you visualize it. And notice I have not said anything about any dimension, right? So this works for any or every Euclidean vector space, all right? So that's the second one. The last one now is pretty straightforward, and I don't need to do much more. I could actually just start with a triangle and have you envision what the result will be, but I want to go back just to this line right here. So I'm just going to call out this line right here. So notice up to this point, we had equality. In other words, all these expressions from the start to the third line here on the right are all equal. So if we now make an assumption about u and v, notice what I said here is that I made no assumption about how these two vectors are related. So now here, let's take a look at this. So if u and v are orthogonal, Remember, that's that fancy word for perpendicular, or they meet at 90 degrees. What do we know about the dot product? Well, the dot product has to be 0 because the cosine of 90 degrees is 0. So then if we drop this 0 in the middle of our expression, look at what happens. So that's true, but the big consequence now is this. The norm of u plus v squared is just equal to the norm of u squared plus the norm of v squared. So that's kind of the algebra. Now let's wrap it up and draw a picture. So if u and v are 90, are orthogonal, meaning the angle between them is 90 degrees, then my picture now would look like this. Let's say I might have u going due north, and then maybe v is over here. And when we do u plus v, I guess if I, yeah, so either way, let me, actually, yeah. Just to, because I want my, it doesn't matter algebraically, but let me be consistent with what I did earlier. So let's say this is u. There we go. So then you got u and then v, so it would be this one. And let me move over my label for u a little bit more. Yep. And then, yep, so we got v there. And then now this will be u plus v. And if I now just look at the magnitude of those vectors, not so much their direction anymore. And if this is now 90 degrees, this, what we wrote down, is just the vector version, the Euclidean version of the Pythagorean theorem. Yeah, so this is the famous Pythagorean theorem, and there you go. So we just kind of, you know, proved three. I would classify them as immense properties that come from the simple dot product and the simple notion of length. But there, as you know, you might not think the Cauchy-Schwarz is important. You might think the triangle inequality, but I guarantee that you have a higher regard for the Pythagorean theorem. It's something that I know you've used, maybe not in this version, but in some other versions. You might, you know, express how grateful you are to Pythagoras for coming up with this result, right? So there you go. So just three key results that involve, again, the dot product and the magnitude. Who knew, right? Well, let's see if we can continue discovering cool relationships, and I'll see you in the next video.